Here we're told we have a steel rivet with a mass of 2 pounds mass, initially at 1,000 degrees Fahrenheit, and it's placed in a large tank containing 5 cubic feet of liquid water, initially at 70 degrees Fahrenheit. So let's go ahead and just draw that out. We have this large tank of water. There's a steel rivet in here. And eventually the rivet and water cool back to 70 degrees Fahrenheit as a result of heat transfer to the surroundings. Taking the rivet and water as the system, so let's go ahead and make that our system. Determine the heat transfer in BTU to the surroundings. So I'm going to just go ahead and draw the heat transfer going in, but we expect it to be negative since the heat transfer really is going out. And we're also given the specific heat for steel in the problem statement. Okay, so this is going to be a first law type of problem because we're seeing a change in the internal energy of the water and the rivet, and also we're interested in the heat transfer here. We're trying to solve for the heat transfer. And heat transfer is occurring because of the change in internal energy of the rivet and the water. And there's no work being done here because the container is not changing. There's no piston or anything. There's no paddle wheel, no electrical work, no springs or anything like that. So let's go ahead and write the first law for that system. I'm just writing it as plus the work done on the system. And then let's evaluate what some of these terms are. So first of all, the work done on the system is 0 because, again, there's no pressure work being done. There's no electrical work or anything like that. The change in total energy of the system will be the change in internal energy plus the change in kinetic energy plus the change in potential energy, all of the system. But there is no change in the velocity of that system or change in elevation, so the kinetic energy and potential energy changes are 0, so we're just left with the change in internal energy of the system. Now the system consists of the water and the steel rivet. So I'll break up the change in internal energy of the system into both of those components. And I'll further go on to say that the change in internal energy of the water, I'm going to assume that it's an incompressible substance with a constant specific heat. So that'll be the mass of the water times the specific heat of the water times the final temperature of the water minus the initial temperature of the water. And then I can do the same thing for the steel, which is also assumed to be incompressible and with a constant specific heat. Okay, so let me write down those assumptions. So as we go from this step to that step, we're assuming that water, let me put a little bullet point here. So assume water and steel are incompressible and specific heat, and the specific heats are constant. So the incompressible assumption is very likely to be a very good one. Water, liquids and solids like steel, they're very nearly incompressible. So that's always a pretty good assumption. As far as assuming that the specific heats are constant, that one's a little more questionable, especially for the large temperature difference for the steel. Initially that's at 1,000 degrees Fahrenheit and it goes down to 70 degrees Fahrenheit. So that's a pretty big temperature range. So assuming that steel specific heat is a constant is a little more questionable. We're still going to make that assumption here, but we have to recognize there's going to be some error as a result of that assumption. So just recognize that, but we'll assume it's constant for this problem. The other thing is the heat into the system. That's a question mark. That's what we're trying to solve for. Okay. So the next thing to do is to simplify this. One of the things that we're told is the water is initially at 70 degrees Fahrenheit and eventually it cools back down to 70 degrees Fahrenheit. So the final temperature of the water and the initial temperature of the water, those are the same. So this actually is 0. So it's 0 since T initial and T final for the water are both at 70 degrees Fahrenheit. So that one goes to 0. So we don't even have to worry about the water in this. So in the end, the Q into will be the mass of the steel times the specific heat of the steel times the change in temperature of the steel. Now we're given most everything we need in this. So we're told the mass of the steel is 2 pounds mass. We're told the specific heat of the steel is 0.11 BTUs per pound mass per degrees Rankine. We're told the final temperature of the steel is 70 degrees Fahrenheit, and the initial temperature of the steel was 1,000 degrees Fahrenheit. Now note, you don't need to change the degrees Fahrenheit to degrees Rankine here because we're dealing with the temperature difference. And a change of 1 degree Fahrenheit is the same as a change of 1 degree Rankine. So even though this is degrees Rankine here, it's totally fine to leave this as degrees Fahrenheit because we're just dealing with a change in temperature. If you're not really certain about that, you feel a little uncomfortable, it's totally fine to change this to degrees Rankine and then do it that way. That's perfectly fine. But what you'll find is that if you add in a constant here and then add in the constant here, the two constants will subtract out, so it really doesn't matter. Anyway, we can do that calculation, and what we'll get in the end is the energy transfer via heat transfer comes out to be minus 205 BTU. So it means that, in fact, we have an energy transfer out of the system, since it's negative, of 205 BTU. All right, we'll end the example there.